So in the last lecture we have seen that this ordinary differential equation is nothing but the relation between the dependent physical quantity with respect to the independent physical quantity. Now there is some general form of the first order ordinary differential equation. So let me tell you how it is. So the general form of ordinary differential equation is dy by dx plus pxy is equal to q of x, which means that this p and this q, these are the functions of only x, and y is also the function of only x. Now suppose if I take the homogeneous equation of this first order equation. So what is mean by homogeneous equation? If this right hand side is 0, then this equation is called as a homogeneous equation. So let me write the homogeneous equation. So plus p of x y is equal to 0. If I collect the y terms on one side and x terms on the another side, and now if I integrate this equation, so integrating dy by y is equal to minus integration of px dx. So this integration and derivative will get cancelled, and I am going to get y is equal to e raised to minus integration of px dx plus log c. Now let us multiply by this integrating factor to this equation number 1. So equation number 1 will be dy by dx plus p of x into y into this integrating factor e raised to integration of px dx is equal to q of x e raised to integration of px dx. To solve this equation, now let us integrate, or let us take a derivative of one more term, which is y e raised to integration of p of x dx. These are just the some mathematical arrangements we are trying to do, because we want to solve this general form of this equation and give it a particular form. Okay, so just take a derivative of this new term y into e raised to integration of px dx. So whenever there is a derivative of the two terms which are multiplied to each other, then we will write it here like first term into derivation of the second term e raised to integration of px dx plus the second term e raised to integration of px dx into the derivative of the first term, that is dy by dx. So let us take derivative of this y into p of x into e raised to integration of px dx plus e raised to integration of px dx into dy by dx. So taking common e raised to integration of px dx, the remaining terms will be yp of x plus dy by dx. Therefore, so e raised to integration of px dx into p of xy plus dy by dx is nothing but y into e raised to integration of px ds. So d by dx of y e raised to integration of px dx. So why we have done all these mathematical operations? We just want to remove the term dy by dx plus p of xy by this term. Okay, Now putting the value of this in this equation, so it will be d by dx of y e raised to integration of px dx is equal to q of x e raised to integration of px dx. Now again taking integration on the both the sides, we will get, so integration of d by dx of y e raised to integration of px dx. Now if I take this integrating factor on the right hand side, I am going to get y is equal to e raised to integration of minus p of x dx integration of q of x e raised to integration of px dx into dx plus c into e raised to minus integration of px dx minus integration of px dx. Okay, so this is in the form of y is equal to, or I can write this equation as y into some integrating factor is equal to integration of q of x into integrating factor dx plus some constant c. So this is called as the solution of the first order ordinary differential equations. This was all about the mathematical operations. So this is the general form of the first order ordinary differential equation, and the solution of the first order ordinary differential equation can be in this can be stated in this form. Okay, so which is y into integrating factor is equal to integration of q of x into if dx plus c. Let us see the steps involved in finding the solution of the general form of the first order differential equation. So we have taken the ordinary differential equation, we have taken its homogeneous form, right hand side is equal to 0, that is called as a homogeneous form. Then we have calculated the integrating factor, and then finally we have got the solution in a form of a integrating factor. So these are the steps which are generally involved in finding the solution of the general form of the first order differential equation. Now let us see how we can apply this formula for the solution of the first order ordinary differential equation to evaluate the values of the physical quantities. We know that whenever we consider a heavier nucleus, so this heavier nucleus is very unstable due to the more number of protons and neutrons present inside it. Okay, so the more number of protons and neutrons are present inside the heavier nuclei. Heavier nuclei is like uranium 92. Okay, so these are called as a heavier nuclei. So this in this heavier weight nuclei, more number of protons and neutrons are present, and due to the Coulombic repulsion is there, and much more alpha, beta and gamma radiations are emitted to attain the stability by this nucleus. So this process is called as a radioactivity. We know that the radioactivity is emission of the alpha, beta and gamma rays by the heavier nuclei, and the heavier nuclei emits alpha, beta and gamma rays due to the instability of the nucleus. So the radioactivity of the element at a particular time t, or the number of radioactive atoms present at a time t, is directly proportional to the number of atoms present at that time. Okay, and this lambda is a radioactive decay or the proportionality constant, and this negative term indicates that as time increases, this number of atoms goes on decreasing. Okay, so if I want to take it in a this general form of the first order differential equation, in a radioactivity, number of atoms present at time t, or the radioactivity is directly proportional to the number of atoms present at that particular time, and the equation can be written as dn of t upon dt is equal to minus lambda into n of t, where lambda is the proportionality constant, also called as the radioactive decay. Okay, so taking the n terms and the t terms on the each side and taking it in the general form of the first order ordinary differential equation, I can write the same as dn of t upon this n of t minus lambda t. Integrating the equation on the both sides, what we get is log n is equal to minus lambda t plus c. Okay, so when you want to remove this log, I will take the equation as n is equal to n0 e raised to lambda t plus c. So which also means that I can convert this equation into this c1 e raised to minus lambda t. Now if n0 is the number of atoms present at a time t is equal to 0, I can replace this c1 by n0. Okay, and then I can write n is equal to n0 e raised to lambda t. So by using the first order general form of the first order differential equation and going by the steps which we are given previously, okay, by taking the integrating factor and taking it into the general solution form of the integrating factor, we can calculate the number of atoms which are responsible for the radioactivity. We can also calculate the radioactive decay. So this is the application. So this is how we apply the ordinary differential equations in physics.